Before we dive into records, let's understand some of the problems that they try to solve. Suppose we have a data type named person, which is defined like so. You can construct a person by providing a string and int to the constructor, where the string is intended to represent the person's name and the int is intended to represent the person's age. These are said to be positional parameters, because when using the constructor, you must make sure the string always comes first and the int second. Otherwise, the compiler will complain and not let it type check. Now suppose that we want to write functions which just operate on a person's name or age. So they take a string or an int as an input parameter rather than the whole person. Something like the greeting function here, which would just take the name of the person as a string and respond with a greeting of hello. Now obviously we can't pass a person to this function, we need to extract the name from it and then pass the name. What we need to do is write what's known as a getter function to retrieve the value from within the data type. We would write that function like so. To retrieve the name from a person, we write the function called getName that takes a person and returns the string value of the name. The logic is simple. It just deconstructs the person in the pattern match and returns the field in the first position for a person. We do the same for the age, except this time we return the second positional element of a person, and then we can use the functions like so. And what happens when we need to update a person? Let's say their age goes up by 1 year. Well, in Haskell, we know everything is immutable, and so we cannot actually change the value directly. The way we do things is shown by the agedBy1 function. Here, we are having to deconstruct the person and all of its fields, and then copy the values over and change the one field that we want to change. Because everything is immutable, we are not actually updating the value. That's why I put update in quotes here. Instead, we are creating a new person and returning that with the age set to the required value. When we call the function, everything works as expected. Now this is all well and good, nothing really new here, and things are manageable because a person only has 2 fields. But you can imagine that if we had a data type with many fields, say 5 or 6, it would quickly become annoying to have to write this type of code for each of our custom data types. Getters and custom update functions would soon become a real pain to maintain. This type of code is known as boilerplate code. It is necessary but very tedious to write. Records offer us another way of dealing with the fields of a type. Instead of working with the fields positionally, like we have seen so far, we work with the fields based on custom labels which we provide. A label is just another word for the field's name. We do this by changing the way we define the custom data type. Let's explore this further. I've created a new type called person_r. The R stands for record here, to avoid a name clash with the previous person type we created. We provide a constructor just like before, but instead of giving types in a space-separated list like we did before, we use this new syntax to define labels for each field as well as its type. We place the field label definitions in between the curly braces. For each field, we give the name of the label and its type using the double colon notation that we are used to. So we have person name as the first label, which is of type string. Each field is separated by a comma, and conventionally in Haskell you have leading commas like so. You could place the comma at the end of the line if you wanted, but Haskell convention is usually to place it in the front. The second field is called person age and is of type int. When we define our data type like this, it is said to be defined as a record, or sometimes it is referred to as being defined using field naming syntax. Let's see how we can construct a value of person r. We can construct a value just like before in the positional syntax, or we can use the field naming syntax to construct a value like we have done here with Elizabeth. The definition of the value is similar to the definition of the type in that you use curly braces after the constructor and place the field names within the curly braces separated by a comma. When defining the value, we obviously provide the actual values which are of the correct type for each label. You can see that the position of the definitions does not matter here. We are giving the person age first and then the person name. This is because the values are given based on the field's name rather than their position. Ideally, you should follow the convention of placing each field on a new line and having a leading comma, but I've had to show the code like this just to save space on the slide. And when we try to view each of the people in GHCI, we can see a slight difference. Satoshi appears in the positional style because that is how we defined the person data type. However, Boris and Elizabeth appear in the record style. Even though we defined Boris using the positional syntax, it still appears as a record because that is how the data type was defined. One of the benefits of defining your data types like this is that Haskell will generate the getter functions for you, and so you get them for free. This means you do not have to write any boilerplate code for the getter functions. They are just immediately available for you to use. Haskell will name the getter functions with the same name as the fields themselves. We can see the type of these functions in GHCI by using the :t command, and they are immediately available for us to use, as you can see here. There is also no need to write functions to specifically update a field, because with records you get a special syntax which allows you to do that more easily. So over here we are creating a new record called Boris plus 1, which is defined as the old record Boris, except the field named person age has its value changed to whatever the previous age was plus 1. We are using the person age getter function here to get the current age. We only need to provide the values for the fields we want changed. Any other field which we don't provide a value for will have the same value as the original record we are updating. Remember, everything is immutable. We are not changing the value of Boris, but rather creating a new person R based on the original values from Boris. You can provide new values to multiple fields at a time if you want, by separating each field value definition with a comma, just like the syntax we've been using so far with records. I've not shown that here, but it should be pretty easy to see how it would work. As you can see, the value of Boris plus 1 is just as we expected, the age incremented by 1 year. One of the pitfalls of using records is that if you have two different types defined in record style, and the fields of these different types have the same name, there will be a compiler error thrown. So, for example, if I defined another record type which had a field called person name or person age, the compilation will fail because the compiler will have tried to create two person name getters and two person age getters, one for the person R type and one for the other one. And obviously this won't compile because you cannot have two separate function definitions with the same name. It causes a name clash. The common way of dealing with this is by putting a prefix before the field names. This is why I put person here before the name and age, to show you how you can avoid this issue if it crops up. There are also other ways you can deal with it, such as by using language extensions, but that is beyond the scope of this beginner course. For now, stick to prefixing your field names with something unique for that record type, like the record type name, to avoid the issue. So, in summary, records allow you to address the fields contained within your custom data type by their name rather than by their position. Records can make your code more readable and save you time by stopping you from having to write the boilerplate code for the getter functions and for the update functions. Instead, you can rely on the getter functions which are generated for you by the compiler and the update syntax which records allow you to use. Just for completeness, I want to show you that you can define your data types using record syntax even when you have a sum type. Suppose we have a dog breed type, a cat breed type, and an animal type. The dog breed and cat breed definitions are simple, but the one for animal uses record syntax. We have two constructors for the animal type, a dog and a cat. For a dog, you need to provide a name, age, and dog breed. For a cat, you need to provide a name, age, and cat breed. Things are very similar to a regular sum type. We just use the pipe to separate the choice of constructors which can be used to create the animal. And the record syntax for each constructor is just as we saw before. And we define two animals, Fido, which is a dog, and Felix, which is a cat. We can see the different getter accessor functions which are generated by Haskell here. They all take in an animal, and then return the type of the field. You will notice that the name and age functions will work with any animal, since their types are exactly the same for a dog and cat. They are both string and int respectively. However, we have had to add the prefix dog to the dog breed and the prefix cat to the cat breed. This is because the types for these fields are not the same, and so we need a different name for them so that Haskell generates the getters with different names too. This avoids the compilation error that would occur if they had the same name, since there would be a name clash. And we can use the getter functions as you would expect. But if we try to use the dog breed getter method on a cat, or the cat breed getter method on a dog, we get a runtime exception, because obviously a cat, even though it is an animal, does not contain a field of type dog breed, and similarly, a dog, even though it is an animal, does not contain a field of type capRead. Be careful of misusing the generated getter functions and ending up with a runtime exception like this. Well, there you have it. That is pretty much everything I wanted to cover for records. This video is a clip from a longer video for beginners starting with Haskell. Check that out if you would like to see all of the content. Also check out the entire Introduction to Functional Programming with Haskell course on the Learn channel. See you next time.